Picture this: a freight train stretching over a mile long, weighing 400 tons just for the locomotive alone, thundering down the tracks at 70 miles per hour. That's roughly 16 million pounds of pure momentum barreling forward with enough kinetic energy to level a city block. And yet, when the engineer needs to stop, this mechanical monster doesn't screech to a halt in a shower of sparks. It glides to a controlled stop with precision that would make a luxury car jealous. No grinding metal, no emergency chaos, just smooth, calculated deceleration. Today, we're breaking down how locomotives actually stop. And I promise, after this video, you'll never hear a train brake the same way again. Early locomotives faced terrifying limitations. They relied purely on mechanical friction brakes, basically wooden blocks pressed against metal wheels. Catastrophic failures were common, from runaway trains to brake fires, especially on long mountain descents where brake components would literally catch fire from the heat of constant friction. The 1920s and 30s saw the introduction of air brake systems, but even these couldn't handle the massive kinetic energies of modern freight trains. Steam locomotives faced additional challenges, with brake fade during extended braking periods, making long mountain descents particularly hazardous. The real breakthrough came in the 1960s, when electric and diesel-electric locomotives adopted regenerative braking concepts from streetcar technology. Engineers realized that traction motors could work in reverse. Instead of consuming electricity to create motion, they could consume motion to create electricity. This wasn't just an improvement, it revolutionized train braking, shifting from destroying energy through friction to harvesting it. Modern freight locomotives can generate enough electricity during braking to power a small town. The evolution continued through the 1980s with computer-controlled dynamic braking systems, integrating with traditional air brakes to create redundant, fail-safe stopping mechanisms. Today's locomotives use sophisticated algorithms to balance electrical generation, heat dissipation, and mechanical braking. But the core principle remains: turn motion into electricity, electricity into heat, and distribute that heat safely. Every locomotive braking system operates on four fundamental forces working in harmony. First, dynamic braking, where traction motors become generators, converting kinetic energy to electrical energy. Second, pneumatic braking, compressed air systems applying mechanical force to brake shoes and disc brakes. Third, distributed load, spreading braking force across multiple axles to prevent wheel lockup and maintain control. And fourth, heat management, safely dissipating the enormous thermal energy created during deceleration. Think of locomotive braking like a sophisticated energy conversion factory operating at railroad speeds. When dynamic braking engages, electrical resistance increases proportionally to the locomotive's speed. When air brakes activate, mechanical friction supplements electrical braking for maximum stopping power. The faster the locomotive moves, the more electrical energy the motors can generate, creating natural speed-dependent braking force. You've probably assumed trains stop like giant cars, just bigger brake pads pressing harder against bigger wheels. That explanation misses the revolutionary part. Locomotives don't just destroy their momentum through friction, they harvest it, converting forward motion into usable electrical energy before finally dissipating it as controlled heat. It's not braking, it's energy recovery on a massive industrial scale. Let's dive deeper into dynamic braking. During normal operation, traction motors receive electrical current and create magnetic fields that turn the wheels. When dynamic braking engages, this process reverses completely. Wheel rotation drives the motor armatures through existing magnetic fields. This generates electrical current. The locomotive literally becomes a power plant powered by its own momentum. This electrical energy flows through resistor grids mounted on the locomotive roof, converting electricity to heat. The physics here are fascinating. A 400-ton locomotive at 70 miles per hour carries approximately 89 million joules of kinetic energy, equivalent to about 25 kilowatt-hours of electricity, enough to power an average home for nearly a day. Dynamic braking can handle 60 to 80% of this energy conversion, with traditional brakes managing the remainder. Those resistor grids can dissipate up to 4,000 kilowatts of power, comparable to a small industrial power plant. Unlike friction brakes that provide constant force, dynamic braking force increases with speed. At high speeds, motors generate maximum electrical resistance and braking power. As speed decreases, electrical generation drops, requiring increased air brake application. This creates a natural transition from electrical to mechanical braking as the locomotive slows. The pneumatic systems are equally impressive. Compressed air systems operate at 90 to 110 pounds per square inch throughout the entire train. Consist. Counterintuitively, air brake application is actually the release of air pressure. A fail-safe design, meaning loss of air pressure, automatically applies brakes. Brake cylinders convert air pressure into mechanical force applied to brake shoes or disc brake calipers. Modern locomotives use both tread brakes, shoes against wheel surfaces, and disc brakes for maximum stopping power. Freight locomotives typically have 4 to 6 axles, each with independent brake control and dynamic braking capability. Computer systems monitor wheel slip and adjust braking force to each axle individually, preventing wheel lockup that could cause flat spots, derailment, or loss of adhesion. Load sensors adjust braking force based on locomotive weight and cargo distribution. The integration between systems is where the real magic happens. Sophisticated control systems blend electrical and pneumatic braking seamlessly. At high speeds, the train relies primarily on dynamic braking with minimal air brake application. At medium speeds, it uses a balanced combination of both systems for optimal stopping distance. At low speeds, it switches to primarily air brakes as dynamic braking effectiveness decreases. And in emergency situations, it applies full air brakes with maximum dynamic braking for the shortest possible stopping distance. Let's see this in action. When an engineer moves the brake handle from run to brake position, computer systems immediately assess speed, weight, grade, and weather conditions. Dynamic braking engages first. Traction, motors switch to generator mode within milliseconds. Air brake application follows, with graduated pressure increase based on the desired deceleration rate. Descending steep mountain grades presents the ultimate test of locomotive braking systems. Dynamic braking prevents brake shoe overheating that could cause brake fade or fire. Those resistor grids glow red hot, dissipating millions of watts of thermal energy into the atmosphere. Air brakes provide backup and fine control, but dynamic braking does the heavy lifting. In emergency situations, the process bypasses graduated control, applying maximum braking force immediately. All available systems activate simultaneously. Full dynamic braking plus maximum air brake pressure. Wheel slip detection prevents lockup even under emergency conditions. Modern locomotives can stop from 70 miles per hour in approximately 1 mile under emergency braking. Weather creates additional challenges. Rain, snow, and ice reduce wheel-to-rail adhesion, requiring modified braking strategies. Sanding systems apply sand to rail surfaces to increase friction during braking. Computer systems automatically adjust braking force to prevent wheel slip on contaminated rails. Dynamic braking remains effective regardless of rail conditions, since it doesn't depend on wheel-to-rail friction. Every time you watch a mile-long freight train glide to a stop at a crossing, it feels like it's defying the laws of momentum and mass. But it's not breaking physics. It's using them in the most elegant way possible. Those locomotives aren't just stopping. They're harvesting their own kinetic energy and converting it into controlled, manageable heat. To me, that's the real beauty of locomotive engineering. Not brute force friction, but sophisticated energy transformation. It's a rolling power plant that can switch from consuming electricity to generating it in milliseconds. The same motors that accelerate hundreds of tons up mountain grades become the primary stopping mechanism on the way down. And now I'm curious, have you ever wondered how those massive locomotives actually get all that power to the wheels in the first place? The physics of traction and adhesion between steel wheels and steel rails is even more fascinating than the braking. I've already made a video about that. Check it out now.